Recording's rolling. It is Wednesday, April 2nd. I see already some of you guys have turned in this page. So we got circuits on one side. We've done about half of these together in class over the last week. And on the other side is the Kirchhoff page. So 4 Kirchhoff tables, some waterfall models. Right? And we did go over all these together. Right? So you guys turn that in. I'll be scoring those, get those in the grade book. But main thing today, you guys have this page in front of you. So what is the resistivity of Play-Doh? Because Play-Doh does conduct electricity. Oh, now I can show that to you guys and we'll get to the details about how to quantify how well does it transmit electricity. So I've got cell phone charger. Okay, cell phone charger, how many volts is this?
5.
Yeah, it should be 5 volts across the lead approximately. I'll measure that with the multimeter pretty soon, but I just want to show you guys this first. Ooh, here, got this. Let's get some dough going. Got some dough. Okay. Now, what I'm doing right now is splitting the dough. This is not part of your lab. You don't have to do this, although you could if you want to. I have a bunch of LEDs back there, light emitting diodes. And then what I'm going to do is take this LED and bridge a gap across, make a bridge across this gap. There you go, like that. Thank you. Like that. All right. Then take the leads from here. Did I get that right? All right. Is this plugged in the right way? Yeah. Red one's long. Let me try a different one. So I have a different LED right here. Some of these are gone poof. Let's try this. Okay. Also, LEDs, you might notice one wire is a little bit longer than the other. That's the positive side. Now the LEDs only work one way. And that's in contrast. The Christmas lights work both ways. So Christmas lights. Oh wait, why isn't this turning on at all? Oh, there you go. Sort of. Okay. Like the Christmas lights can go both ways. The LEDs only work one way. So we get the red lead on the left side. And there it is. You guys see it light up? Boing, boing, boing. So open circuit, no electricity flows. Closed circuit, closed. And you guys see how the only way it would light up like it is right now is if there is current going across that LED, across that bridge. Okay. So and it has to be then going through the dough. So this dough is definitely conducting electricity, isn't it? You see the dough is definitely conducting electricity. Okay. So next question is how well? That's the question for you guys today. So suppose they have a wire. Guys, look here. Suppose they have a wire made out of aluminum and a different wire that looks exactly the same, same length, same cross-sectional area, but it's made out of copper. Do you think those two wires transmit electricity differently?
Yes.
Yeah. I think the copper one is a little bit more conductive than the aluminum one. Right? But regardless, here's a model right here. Let's get this clear. So suppose you have a wire, or this could be your dough cylinder today. So this could be a cross section of a wire or a dough cylinder. It's the same idea. It's kind of like a wire made out of Play-Doh. Oh, guys, everybody look here. The longer the wire, the more resistance from it in. Does that make sense? Like if you have a wire that's 1 kilometer long versus 2 kilometers long, the longer the wire, the more resistance. What about this? How thick is the wire? This cross-sectional area. Does it make sense? The thicker the wire, the less the resistance is going to be. That's why there's an inverse relationship here. And there's one more detail. Guys, what Greek letter is this right here? Here, rho. And today it's going to represent resistivity. Now, a few weeks ago it represented density, but today it's resistivity, which is the reciprocal of conductivity. So same idea there. Okay. So how can you get that? Well, if you can get resistance, cross-sectional area, and length, you could feed it into this formula and calculate the resistivity, which is a material property. As copper has some resistivity, aluminum has some resistivity. You can Google the answer to the question today. What is the resistivity of Play-Doh? You can type that question into Google, you'll get an answer. And if you do these measurements and calculations correctly, then it should be pretty close to that Googleable answer. So good left to right here. We're working up towards very last column says what is rho? That's the resistivity. The unit, by the way, is ohm meters, right? For how conductive or resistive in this case is some material. So what's the diameter of your dough cylinder? Could you guys get a ruler? Yeah, go borrow this ruler. Could you guys measure the diameter of your dough cylinder? Guys, suppose it was 2 centimeters. Should I write 2 here for 2 meters? Does that sound right? 2 meters? No, as 2 meters is, well, taller than I am. So 2 centimeters. would be how many meters? 0.02, right? You have to roll it back 2 decimal places because 100 cents in the dollar. Okay. Now, if you know the diameter, could you calculate this cross-sectional area? Okay. And I gave you the formula right here. So you guys know area of a circle is pi r squared. So if you play off diameter, it's pi over 4 times diameter squared. Okay, same thing. Okay. Could you guys measure the length in meters? Suppose this dough cylinder was 8 centimeters long. Do I want to write 8 right here? No, because that would be the width of the room. I don't have one that long. But could you write 0.08? Okay, that would be more reasonable. Right? If you write 0.2, that's like 20 centimeters. That would be the closest to room. Okay. Next one, voltage. Now it's time for the multimeter. If you want to do voltage, remind you guys how this works. I'm going to leave the black lead in COM, take the red lead, switch over to voltage. Okay. And say I could wire this up. Okay. Now, right now, this is basically your setup today. You don't need the LED, like I was saying. Okay. But I'm going to switch this to DC volts. Take the 2 leads to the voltmeter. Hey guys, the voltmeter, do I connect this in series or parallel to get the voltage? Let's do parallel. So there's my circuit right there. Guys, the circuit's already going. There's already electricity flowing. I can't see it, but I know it is. Now if I go end to end, I should get, let me press this right up against these leads here. This should be about 5 volts. Is that not shown? Oh, there it is. 5.0 volts exactly. You guys see 5.0 volts? So if I have that hooked here and here, it'd be 5 volts is what it's going to be. 4.9 volts. Okay. So remember, it has to be in parallel because you're measuring a potential difference between 2 locations. So there's your volt. Should be approximately 5. You might get 5.3, you might get 4.8. Now the current. Now current, I have to make a few changes. One change is I'm going to move this red lead over here. I'm going to switch this toggle to the one that says milliamps. Now, I was trying to figure out, because I couldn't remember from years past, is it actually showing milliamps or is it showing amps? So having done the numbers today, actually it is amps, right? And you guys were treating it as amps the other day, which is actually correct. Right? So it is amps. But I also have to break open my circuit. Guys, look, is there any current flowing right now? No, because it's an open circuit. But if I attach red to red and then black to the other end of this dough cylinder, do you guys see that? Now, this multimeter is about to become part of a circuit because it's now in series, isn't it? Series. Okay, so let's get a number here. Is this going to show me anything? This is a little closer. Nothing at all, huh? There it is. It flashed something. It flashed. Come on, show me any number. Any number. All right, there you go. There's how many amps? So that can be 0.2 amps. Okay. No, really, you want to do it at the end here. I don't know why this is working so well right now. But you might get either 0.1 or 0.2 amps. Okay. You guys saw the flashing number up here. Okay. So that's probably all you're going to get. So this barely works. This lab barely works, but it just does. So you can get 0.1 or 0.2 amps of current. Okay. Is that? Not the best, but it will work. And like I said, if you do everything correctly, you should get a value. It's pretty close to the Google value for the textbook value. Okay. So what we got here? So I just showed you guys how to get voltage, which should be approximately 5 volts. Current, you should get approximately 0.1 amps, maybe 0.2 amps. Okay. Resistance. If you know voltage, you know resistance. Sorry, you know voltage, you know current. Can you calculate resistance? Does that sound like Ohm's law? And I wrote it for. I'm really helping you guys out here. Here's Ohm's law, and I even rearranged it for you to solve for resistance in terms of voltage and current. Okay. You guys have done this before. Okay. Now you have all the puzzle pieces. You just got to put them together. And that's this very last step. This very last step. Resistance from end to end is rho L over A. And that's going to bring us back to the beginning. All right, back here. All right, so here's your setup. Now, do you guys see the setup? Oh, here's the cell phone charger. Here's the dough cylinder. I got one lead here. Here's my multimeter, and you guys see how this is connected in series. What is this showing reading right now? Is this showing reading voltage or current? It has to be current because it's connected in series. Okay. All right. So I'm probably going to leave this slide up while you guys are doing your lab because it's really helpful. So if you know R, L, and A, can you guys calculate rho? I see that. Okay. All right. So I got some videos for you guys. So first, I have a bonus video. All right, so this is not today's lab, but Doug at one shows how to use a breadboard. And right near the beginning, so there's a breadboard. He's making some circuits. Ah, there it is. That's what I want you guys to see. See that little robot? Right. So if you put the components right, you can make a little robot with it. All right, anyway, let's go to today's lab. So hey, look, that looks a lot like what it is. Got a dual cylinder. He's got a voltage source. He's gonna hook this up. Okay, got some current flowing. He's got a multimeter. You guys see connected one end of the multimeter, one lead right there, and I'll take the other lead and I'll put it at different locations. Okay. Oh, now right now, you see a number flashing on that multimeter right there, 7.8 something. Okay, guys, that's 7.8. What is that? Amps or volts? It's got to be volts. How do you know it has to be volts? Yeah, he hooked it up in parallel, right? The circuit is right here. I'm tracing out. Can you see my mouse cursor? Here's the circuit right here. Okay. The multimeter is not part of the circuit. Unless you consider it parallel, it's just reading in parallel. It's saying what's the potential difference between this location and this location, the voltage change. So from here to here, as this current travels mostly along the dough, it changes by about 7.8 volts. Okay. Now throughout this particular lab, he changes. He has sort of an independent variable. He's just changing the length. And now you guys don't worry about that so much. You guys can go from end to end for this cylinder. But right at the end, he makes a change. Oh look, he broke open the circuit. Now there is no current. But there's about to be. Watch how he's going to wire this up now. He's making some changes. You guys see how he just put the multimeter in series with the whole circuit? Now that multimeter is definitely part of that circuit because now the current's flowing through the multimeter. And he's getting, what is that, 13.9? Guys, that's 13.9 what? Amps. Yeah, amps, which is current. Right, there you go. Amps are current. All right, so everything you need, back to the lab area. I will walk around and help you guys out. We might have a few spare minutes. So if you have any questions about anything this week, you guys know you got a quiz coming up on Friday. Or if you want to shock yourselves on the Van de Graaff, that's also been a popular activity for the past last few minutes of class. You guys can shock yourself on the Van de Graaff.
When